Okay, welcome to week 5 of Machine Learning Foundations. We'll be continuing the discussion of linear algebra all through this week and one more week after this. The goal of this week, the lectures in this week is to finally get to the most important theorem in linear algebra, which is the spectral theorem. And we'll get to this in a more general form, not necessarily real vector spaces, but we'll look at this theorem in the context of a complex vector space. And the important class of matrices that generalize real symmetric matrices is Hermitian matrices. So we will prove spectral theorem in the context of a Hermitian matrix to show that it's the mean result in very simple terms says that every Hermitian matrix is orthogonally diagonalizable. So as a gentle start in this lecture, we'll look at complex matrices, complex vectors and complex matrices, and try to understand how we can define inner product between two complex vectors in the more natural form. And then we'll also define what it means to take the conjugate transpose of a complex matrix and use this notion of conjugate transpose to define a Hermitian matrix. So we'll denote this by Cn. This is the complex counterpart of the usual Euclidean space, n-dimensional Euclidean space Rn. So when I say x1 up till xn belongs to this, then what I am saying is each xi is a complex number for I equals 1 to. Now, this is something that you may already know. How do you addition of complex numbers? If I have a plus ib plus c plus id, then I add the real and imaginary parts. And multiplication also. This will be AC minus PT plus I into BC plus AD. This is something that I hope you are all familiar with, so I am not going to spend too much time on this. Now, the important thing to understand is this complex conjugate. Complex conjugate of a complex number A plus IB is A minus IB. The way to understand this is if you have a complex number, you can use the polar coordinates to represent A plus IB as r e power I theta. And now this is the real axis and this is the imaginary axis. And now the conjugate would be written as A minus IB. This is the conjugate denoted like this, and that can be represented as r e power minus I theta, where r square is this is nothing but the length of this vector. Now, you can take linear combinations as before, linear combinations with a slight tweak. So, if I write C1 V1 plus, okay, let me use X1, Cn Xn equals 0, let us say K. If I take K vectors, not necessarily xk equals 0, then The difference from before is these scalars could be complex numbers. Okay. And these belong to here. Now, the next bit of background to cover is inner product. And also the length, the concept of length of a vector in the complex case. So, recall in Euclidean space, this was your dot product, this was the inner product, and that was used to define the length of a vector. Okay. Now, we cannot use the same definition in the complex case. Why? Because it does not make intuitive sense. Take an example. For example, using star, what would be the length of 1 I? This would just be 1 square plus I square, which would just be 0. Okay. So, in the case of a complex vector space, define the inner product a little differently using what are known as conjugates. As if I want x dot product with y, that will be x bar transpose y, which is like I take the conjugate of the first one and multiply with the second one. The important thing is this relation, very important note. Using this, we can easily see that x bar transpose y is definitely not equal to y bar transpose x. I mean, if you want, take for example, x is 2 minus I, 1 plus I, and y is, I mean, if you take real numbers, if you take real x and y, then obviously this relation holds. So, you need to take complex numbers. Now, check x bar transpose y is not equal to y bar transpose. Now, how do I define the length of a complex vector? The way I do it is, if x belongs to this, define the length as x bar transpose x. Now, with this, you know, the length of 1 comma I, what would this be? This won't be 0 when you take the conjugates, but you can check that this turns out to be square root 2, and it's not a 0 length vector, which coincides with our intuition. So, 1 comma I is not a 0 length vector, and so our definition, if that vector is 0, otherwise we won't get the 0 length vector. Now, you can check this. I am going to just check these. 1, this can be done by definition. If I take x dot y is y dot x conjugate, and if I do x dot some constant times y, then this is going to be just that constant times x dot y, simply because you are taking the conjugate of the first component in the inner product, and but the same is not true of this one. When you do it like this, the constant comes out as a conjugate. Okay. So check these can be verified by definitions. Yeah, check this using definition of dot product, inner product, that is x dot y equals x bar transpose y, summation x bar I to y I equals 1 to n. Now, given this, we define what is called a conjugate transpose. Everybody knows transpose, so here you add the conjugate. So A star is that matrix which is the conjugate transpose of A, and it is defined as A star equals, you can do this in either order and they lead to the same solution. As an example, suppose A is this 1 plus I, 3 minus 2I, 2 minus 4I and I. If you have this, then what is A bar? A bar is just 1 minus I, 3 plus 2I, 2 plus 4I and minus I. And A bar transpose A star equals A bar transpose equals we would get the same result by transposing first and then taking the conjugate. Get the same result, that won't change. Important remark, for a real matrix, A star is nothing but A transpose, because for a real number it is its own conjugate. Okay. Now, some claims again this can be checked. Check. These are just the equivalent of transpose that we have. If I do A star and do another star, what I recover is this, and AB star is B star A star. Now, in the real case, what you would get is the equivalence is A transpose equals A, and A B transpose is B transpose A transpose. Just reiterating the inner product, so that I have it defined in one place. X dot y is x bar transpose y. So, this is x 1 bar y 1 blah 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 x n bar y n. This can be written as x 1 bar until x n bar y 1 to y n. But this is the same as x star into y. Okay. So, x dot y equals this. The last bit of definition before we close this lecture is what is called as a Hermitian matrix. Matrix A is Hermitian. This is the equivalent of symmetric matrices if A star equals A. Hermitian matrices are the equivalent of symmetric matrices in the complex vector space. Okay. For a real symmetric matrix, you have A transpose equals A, and for a Hermitian matrix, if I take the conjugate transpose, it's the same. So, a quick recap before I end this lecture. What did we look at what are the contents of this lecture at a very high level? We understood how we can define the inner product between two complex vectors, and this involved some change. In particular, we had to do a conjugate operation instead of just the transpose. We had the conjugate operation in addition. And the second thing that we looked at was conjugate transpose, the notion of conjugate transpose, which when applied to matrices, we applied it to a matrix, and if a matrix and its conjugate transpose coincide, that's the so-called Hermitian matrix, and it's a very important subclass of complex matrices which we'll be concentrating on, because these are matrices that will be orthogonally diagonalizable, which will become apparent as we go on in this week in the forthcoming lectures.